Okay, time for some hacking. So I encourage you. I would start, for example, for the diffusion to the OpenACC example. Okay, so yeah, I encourage you to start from the diffusion. As I said before, there are two files, for example, the diffusion to the OpenACC CPP or the F90 for those that they want to use Fortran, and the HPP, which is the header file. And the equivalent of the diffusion to the HPP for the Fortran version, I think it's this diffusion to the FO3. So yes, so you see diffusion GPU, copy GPU, and so on and so forth. So I would just leave you to start working on it, and then we can go through it together. So any ideas how you would do it?
Good question.
Yes.
What is the OpenACC data?
Yes. This is whatever is in the section that assumes that this if-def OpenACC data is the data management is done by the OpenACC. So you should copy in your data structures or create and allocate them. Otherwise, if it's not defined, then it is meant to be done by CUDA. So for example, I can show you here that the key difference. So you see that if the OpenACC data, it's basically two versions of the code in the same file. So if OpenACC data is defined here, then you just alloc on the host. Consider this as a standard malloc. So you just allocate your arrays on the host. Otherwise, you have one X on the host, and then you have the X0 and X1 arrays that you exchange every time at the end of each iteration. You allocate them explicitly with CUDA on the device. So the malloc device at the end, it does a CUDA malloc. So yes, it's defined. I mean, I'm compiling the different versions.
So you look in the makefile and okay, makes sense. Okay, thank you.
So yes, here it is. Yeah. So you see, the diffusion to the .openacc. It's the executable. That executable defines the flag. The OpenACC.CUDA does not define the flag. So, but yeah, just start with OpenACC, and I would say the first easy way to go is don't bother with data regions and go in the diffusion to d.hpp, and for each of those loops, each of those functions, you can define the ACC parallel loop or with OpenMP if you like, and just do every time the copy in and copy out, and then you will be always doing the copy ins and copy outs.
But I guess there should be somewhere include OMP.h or something, and if it's that, then we should use OMP or otherwise ACC. Or we can use any.
You can use I think you can use any of them. Hmm?
To use OMP primers, I need to include OMP.h, no? And to use ACC, I also need to include
No, the OMP.h, you need it only when you need to call runtime functions from the OpenMP runtime. Like,
there's also an API. You can use real runtime function acting in more details on that. But practically, if you just use these directives, that's just hints for the compiler. You do not need to
yeah, the only
files with it.
the
in the exercise that we were doing earlier today, it was included in the main.
there is only a complication with OpenMP because I have designed the exercise and the make files having OpenACC in mind. So probably the flags need to change. So if somebody tries, we can sit together and have a look, or with me or Mondes.
But right now you're saying I can just do primers and not care about that.
So I can, okay, let me just then show you, let's go to the solutions and I will guide you a bit through. So, okay. So I would say you could start from a simple kernel, like the field GPU. That's the easiest, right? And only implement the thing at the OpenACC data. Don't care about we will talk about what happens with the CUDA. So for example, here it's just a function that takes an array and assigns a value to it. So you have here the pointer, and here you have the pointer, and here you have the size. So basically you know the shape of the array. So then you should put the directives, and here I'm putting present, but you can also try it with copy in and copy out, and every time copying and copy out. So I don't know if anybody is trying, or if you want me to see how it goes, to show you how it goes. Okay, I will. Okay. So I will start with field GPU, and then pragma ACC parallel loop, copy, this is copy in, copy out of, I would say p copy of v from 0 through n, right? Then I'm going to do the same for this guy here. So here we have copy in the SRC from 0 to n, copy out the DST from 0 to n. And these guys here are 2D arrays. And I'm gonna do ACC parallel loop, and I could parallelize both and collapse them. And now I need to copy in x1 x0 from 0 to nx by ny. So you see you can put expressions here. And for somebody has asked yesterday whether this should be compile time or runtime, whatever. So, and then copy out x1 0 and x by ny. Okay. So let's see how this behaves. So has everybody put the directives at these basic functions?
How can I make the particular program using Directive?
It will make all of them, but then you can pick the correct or the correct one to run. Yeah. Let's see if we are. So it's the OpenACC. Let's see. Okay, and here you get also, when you run it, you get the execution time. This is, as soon as we have a correct program, then we can try larger grids so that we can compare the performance between the different versions. I have, in fact, here I have put up a small table that you can fill in with the actual performance values. So let me check now what the output looks like, whether we have done something. Okay, I think we have messed somehow. This isn't what is supposed to be happening. Let me check. Okay, something's wrong. Has everybody run? Or do you have problems? Yes. Yeah, sure. I'm first. So, okay, here is the. Okay, in the HPP you see those to-dos, so it's where you should go and put the directives. So here is basically the diffusion kernel. So what I have added is the following is a parallel loop. So it's Pragma ACC parallel loop. Basically, is like the teams distribute that we had for OpenMP. And since the next two loops are independent, I'm telling it to collapse the iteration space. Probably you will see it tomorrow. When there are dependencies between the loops, then you cannot do it safely. And even if you have also statements inside here, so then that's not possible. So if they're perfectly nested loops, then it's a good practice to try it, because it may give you better performance results. And then I'm saying, yeah, not always, but it's a good starting point. So
could you also leave out the collapse too?
Yes, you can remove it. It doesn't. So then it will parallelize the outside. Yeah, then it will auto-detect the loops inside, like with the teams distribute, and will if it sees that they are independent, then it will split it in blocks and it will distribute the whole iteration space.
And I could not use the collapse too if in the second line before there would be another.
Here, you mean? Yeah. No, you can't. So if I use collapse, I will get a compiler error here. So they have to be perfectly nested, the loops.
And perfectly nested means like there is no space in between.
No, not space, not space. If I had something like commands, so statements like, I don't know, int or something, yeah.
The same as after the inner loop. You also have nothing to be.
So here, and then if I was using that variable somewhere in here, then I wouldn't be able to do this. I will get an error. So, and then I'm saying, okay, from the x0, I am reading. So I just say copy it in to the GPU, and for the x1, I just need its output. So just copy it out. So
Do you need to specify which?
that's the directions that you've seen before, the map to and map from. What do you mean?
Do you need to specify the 0 to mx times ny?
Yes, because this is in C or C++. Because in C and C++, the pointers are just, they don't have a shape like the arrays in Fortran. So in Fortran, it will be x0. You wouldn't need that specification here.
You could specify if you have a sub or a
Yes. If you.
portion of a area, but you are not necessarily needed in that case. But in C it is.
So yes.
And this is valid also for OpenMP?
Is this valid also for OpenMP?
What do you mean? Which one?
I mean, if I would want to do the exact same thing, but in OpenMP, I will write dash pragma OMP distribute teams. No,
and then the shape of the array.
Teams, distribute.
I think yes. I mean, in C, C++, you have to specify the shape because it's not known. It cannot be known basically.
Okay.
The exact syntax is, I think it's similar, the exact syntax, right, Mandes? For the for the shape of arrays in OpenMP is you again have to use the square brackets if this is
Okay.
what you're asking.
Yeah, I see.
I'm not sure if you really it's necessary. I think you could also leave it out there for
For
normal
OpenMP.
static arrays.
For static arrays, yes, but for dynamically allocated, I don't think so.
That is different.
Yeah.
Then I think there you have to.
And that's because in C and C++, static arrays are a different kind of, it's a different type that has the shape. It's bit low level C, but if you have a static array, it's different from a pointer, although they're treated as the same. A static array, if you do a size of a static array, you will get the size of the whole array. But if you do a size of a dynamically allocated array, you will get, of the same size, you will get the pointer size only. So they're different objects.
And these are not static.
So these are all dynamically allocated. That's why you have to, and then inside this function, you just get, you just get arrays, pointers,
Oh, yeah, you
and
just
their
get
shape.
pointers.
So you don't know how they are allocated.
So I would have to do it exactly like this.
Yes, yes. And then there is the copy GPU, similarly, where you copy from one array to another, then you have copy in the first array here, and copy out destination array. And the correct here would be, well, for OpenACC 2.5, this is like present or copy. So in OpenACC 2, you have to do this, p copy in, p copy out. If it's so that you avoid the additional copies. Otherwise, every time will be copied, every time will be copied out. And you don't want that.
But for the current version we have on Daint,
The Cray compiler is OpenACC 2.0 and won't support any further. But the PGI compiler supports OpenACC 2.5 spec.
so p copy in, and what's the other possibility?
P copy out. So you just prefix it with P.
I would suggest to really use, at least for now, to use p copy in, then you're on the safe side.
Yes.
P copy in, p copy
let
out.
me-
So always use this present or case. You can also do it like he did before, just the copy in, out, but then you risk, if you compile with a compiler using OpenACC 2.0, that it's copying again your data. Maybe also overriding it.
Yeah.
Actually, how can I know if, so p copy out, I of course already have some array on CPU memory. So present, how does it compare if it's really present? If I want to copy it, to update it, or maybe I don't want.
No, the present just means the copy on the GPU. I mean, for sure, on the CPU, you always have the data.
Yeah.
Yeah.
So there is also p copy out.
P copy out just means if there is data on the GPU, use it. If not, you do not have to copy in to the GPU, but anyways, you copy out.
So it seems you always copy out.
Always copy out, right. The question is does something happen at the beginning of this statement, like kernel or data section? Does something happen on the GPU with that data? Is memory allocated? Is the data initialized with the values from the CPU?
But my original solution is you can create a data region outside calling all those functions, copy in or just create your buffers in there, and then use present. So because you know they're present there. So I can showcase this.
So you mean with present, real present, not present or copy in?
Yes, could be also present or copy, but
Right. Yeah.
my
I
original
just want
solution
to-
that you will find in the solution is I can show you exactly. So as not to type. So here I am on the Diffusion 2D OpenACC, and then all the buffers I need is just the x0 and x1, right? So I copy them, and then here inside this block of code, it's happening all the iteration steps. So I copy them before I start any iteration. I copy them in. Well, basically, I'm not copying the x0 because I just need to create it there. And I initialize it inside the GPU. So you need not copy it. You just need to allocate it because this will be basically created once and then you reuse it. You initialize it with a filled GPU, and then you just copy out the x1 buffer, which is your result after you finished your iterations. So you create this data region from here up to here, right? Not up to here, sorry. Up to here. And for this data region, it's basically the lifetime of those two buffers, which is all your computation. So you can put this in this part. So there I'm creating, I know the size of the buffer. I'm creating it for the x0 because I will just initialize it here. Same for x1, but the x1 I need it back. That's why I have put copy out here.
What is this copy GPU?
Which one? Copy?
There is ifdef OpenACC, and then you do copy GPU.
This copy GPU. So the problem is that ideally, in this example, you compute the values of on one array, one grid, and then you swap the pointers and go on reusing what you have computed to compute the next iteration. And usually ideally you would do it with a swap of pointers and go on and go on. But the problem is you cannot actually swap pointers that they are managed from OpenACC runtime. It is dangerous and it can be undefined behavior. So the only way you can work around that is just to do a copy. So I'm going to show you the results, and you will see that this incurs an additional overhead.
But this copy GPU you wrote yourself, or is it some predefined?
No, I've written it myself, and it is in this Diffusion 2D HPP. So let's go and see one by one what they look like. So filled GPU is basically, it fills up the buffer. So let's see how it looks one by one. Filled GPU. So let's just ignore the device PTR directive. So here we have a data region inside, and we have allocated the data, and inside there we know that this pointer, the V, and with this size, this array is present. So we're just saying to the runtime, look, this is present, go on and use that you have in your present table. and fill that array, that loop will execute completely on the GPU. Similarly, yes? Yes, here it is, because it's dynamically allocated, and in the context of this function, it doesn't know what's the shape of this array. It wouldn't be needed only if it was statically allocated. But for yeah, you're right on that. Yeah, you're right on that. But it accepts both. So basically, if it's a present, I think that's enough. Yeah, that's enough. Yeah, those two are enough. Because it's just a pointer. Yeah, for the present. You're right. You're right. But both are acceptable. So
the compiler or something has to check if it's really present?
Yes, because the compiler has a so-called present table which has associations of pointers that their counterpart on the host and their counterpart on the GPU, and then also has the shape information. So it knows that this pointer is this region associated with that pointer is on the GPU, so it will use that.
And we write present to avoid copying.
What? I didn't hear you.
We write this present statement to avoid any copying.
Since we have copied in and did our data management outside this part, then we just say, look, this is present, so just go for it. You could also have p copy in, and if it is present, it wouldn't copy it, as I showed you before. This is what I will give you with the solutions. So
it's essentially an assertion, right? If at runtime it's not present, it will say, you said it was present.
yes, exactly. Exactly, and actually you get this runtime error if you say something is present and you have not copied it in, then at runtime you will get an error that I couldn't find what you say. I mean, for example, V is not present in my table. Yeah, I can show you. I mean, omitting a copy, and so those functions, we have the fill GPU, and then we have also the diffusion, which actually does this stencil computation here, and this is what it looks like. Again, present from the NX and NY is the grid, but in reality it's a one-dimensional array in memory. So here you just say, again I could use present x0 and x1. Probably I have started from a different version that I had before, but it should work even with x0 or x1. Let me just try it. So I can try it out. Let's see if here is everything set up. Okay. So now I'm gonna compile. Yeah, probably I have come into this problem, that's why. So have you tried it and you...
I think you're right.
Yeah, it's only the device PTR or the use device that you don't basically need it. So, okay, I will revert to what I...
In C++, it doesn't complain.
It doesn't complain, but then you will probably have a problem at runtime. But I can just try it right now, because I omitted the... Probably I have come into this problem, that's why I have put the present. Usually, when either when you're working with OpenMP or OpenACC, I mean, at least when I'm doing, I have in my next window, I have the spec to just check, because always there are many small details that you miss.
So it will be more secure just to put this.
So you see here we're getting a runtime error. Variable not found in present table. So that's probably because we didn't have the specification of the size. And this similarly if you haven't just copied in. So now I think I have checked out the original versions with the specification. So okay, let's see, let's compile it again. So, okay, let's run. Has anybody tried to put the directives? Okay. So now you see, I mean, the present was needed. And now what I could do, I could first, as a reference, run the OpenMP version, but I will have to specify the number of threads. I think we have 12 cores. So and now we will increase this to 20. I mean, so as to have quite a large grid, so that it would make sense, I mean, to compare the CPU versus GPU. Yes?
I have a question.
Yes.
Would you show please once again the file Diffusion OpenACC?
Yes. Yes. Yes, where do you want to?
So, where is the create, copy out, and this place?
Yes. It's right at the first to do. I think the first to do you see in the exercises.
Because I got an error that it's x1 is not present.
Have you put in the
Runtime.
diffusion to the HPP in your present statements? You have to put also this specification. So not just present DST or SRC. You have also to put the shape. Have you done that?
I forgot about copy. Yeah.
In all of the exams, also in the probably you see that here. So you have to do present x0 and then from 0 to nx by ny.
Present with the full ranges.
Yes, you have to put the range. Otherwise, you will get this error message, this error message. I tried it before and I got it as well. So has anybody tried to run successfully, except Will? Yes, please. The mic. Just press the button to unmute it.
So in line 48, the ACC data create. Okay, for me it's 48. For you it's 47.
That one.
Yes. Can you say again, what does the create do? I understood it as if the memory is just allocated on the
Exactly.
device and it's not copied over.
Exactly.
Because what I then thought is that if you go up a little bit, for me it's line 35, up, stop.
Yes.
So in line 35, we allocate it on the host, right? I understand that the pointer needs to be there, but I don't know why we need to actually allocate it.
Exactly. That's a limitation, basically. Even if you do a create, there must be a counterpart pointer on the host, even if you don't copy.
I understand the pointer needs to be there. I just don't know why.
It has to be an x0 variable, and that's a double star pointer also on the host. And then even if you don't copy from this to the device, and you just need to do a create, then the pointer has to exist. That's a limitation from the standard. And I suppose it comes from the fact that it has to do a mapping in this table. So it has to do an association between host pointers and device pointers.
So it cannot be a null pointer or point to some fictional value.
I tried to set it. I tried to set it null. It didn't work.
It can be.
I tried. It didn't work. I set it to null, and I got a runtime error.
Okay, so you tried like putting null here, and so you tried that.
Yes.
And okay.
Well, without the next line, right?
Yeah. Okay. Yeah, I haven't tried that, but theoretically, I mean, you have to. There must be a counterpart.
Okay.
Okay. Yes. How to run? So that's a single. Or let me show you the easy way. Go to the job.batch, and here you see the nodes. So just replace this with 1 because this is single node job. And here just remove the rest here. And for the moment, to check that everything works fine, just use this. So srun here, diffusion to d.openacc, and submit this job. No, you need them in your case. For my case, I have just commented out, but you should also uncomment the account, but for my case, I need not. So this should be, if I do this.
And this is one node, right?
Yes. So here is my job. So apparently, if you submit, I should see yours as well.
And the plotting function knows.
Which
I
one?
didn't look into it, but it knows which one to plot. That it always plots the easy one. Is the output overwritten? If I would now.
Yes. It overrides. It overrides the output. Okay, so let's see that everything is fine. Yes, is basically what we expect. So now I said I want to run a large version of the OpenMP.
Can you more your job.out?
Yes.
Yours seems to be faster than mine.
Well, this is a too small test case, so I'm gonna run now for large grids. So I will. Then you can plot from different sizes, and then you can see when starting using the GPU starts to pay off.
Yeah.
I haven't done that, but you can do it. Yes.
Maybe this P copy out allocates memory on the device, and then after it copies the
Yes. Copies back. Yeah. So now I'm gonna just submit the OpenMP version with a relatively larger, with much larger.
What does this weight do?
Basically, this I think you will. Mandus will show you tomorrow. It's you tell. Basically, it's like a synchronization point. For those that they have seen CUDA, it's like the CUDA thread synchronize. So basically, you wait for all the events that they are in all the streams, like copies, kernel launches, copies out to finish, and then, record the time.
So it's like MPI better.
Yes, something like that, yeah. But more tomorrow at Monday's presentation. So it took, oh no, it's on one thread. I need to put more. That's not fair. So, okay, I'm putting, or 24 threads. I will also use the hyper threads, everything.
Now you don't run the OpenACC version.
Yeah, I'm just running the baseline. And then we will run the OpenACC version to see. But you can try different sizes. Every time you increase by one the parameter, the 20, for example, if you do 21, is double the size of the previous because it's exponential. So, for example, here we're using a grid of 130 by 1 mega. So it took 5.6 seconds. So now I will run the single node OpenACC version.
Did we have to do in CPP anything besides create
No, just the. I will show you the weights. I didn't show you that for the times. Yes. So here is the OpenACC version. So it took. Yeah, it's how many times is faster is that? It's like 5 times. 5.5. So let me just show you again the OpenACC CPP. Oh, no, here. So the only thing, okay, you create here the data region. Just to be on the safe side before starting measuring, so as not to start measuring also data transfers, you just do the ACC weight, and this will make sure that all the data transfers will have finished at this point, and then you just start timing. And then again the same here. Okay, this is the results. Okay, and then I can show you how it will look like when you allocate with CUDA. So this is like an example of what to do if I have a part of my application that's optimized and I have written it in CUDA, but I don't want to write the rest of my application in CUDA. I just wanted a single kernel, for example, I needed to be very optimized. So if you're fine with that, I can showcase the next example here. So if you want to, the parts that you need to to chains are those that are basically in the else clause when the OpenACC data is not defined. So there we need to have an additional array, which is our X vector on the our grid on the host. That's why I have this X host. But then we have to explicitly, I mean, it's like we explicitly allocate with CUDA the memory on the device. It's like if you had, for example, you needed write a kernel in CUDA, and then you want to reuse those pointers to do different things on the data, but you don't want to write all your code in CUDA, for example. So here, if you go deeply in the util HPP, I think you will see that eventually it calls CUDA malloc, but that's some C++ that for the moment you don't need to care. So you know that X0 is basically CUDA pointer to the device. So in this case, basically you don't need to copy anything in or out, because you take care of the data management of your pointers. So that's why we don't do anything about when data management is done by CUDA. But now let's go and look how the kernels will look like. So the diffusion, I will start for the simpler one, the GPU. So, okay, so this is a simple kernel, basically, that assigns a value to all the elements of a vector, of an array. You've seen that when data management was done by ACC, we had to specify that the V is present, or do a p copy in present or copy of the V. Now, no data management is needed to be done by p copy out, sorry. No data management needs to be done by OpenACC. So what we need to say is that this V here is a device pointer. So we instruct the runtime that for the kernel you will generate there, the V is a device pointer. So use that pointer and don't try to copy or do whatever. So the same idea happens with the other kernels and also here. So it's a bit simpler how it looks like. And the other advantage that I told you before is that since we're doing our memory management, we'll just swap the pointers. And then just OpenACC will generate the kernel using those pointers. So I don't know, I will let you a bit to just put the statements also yourself.
But where do we get data back to X underscore host?
Yes. I will reply. I'll come this in a moment. I'm just waiting for some time for you to, if you want to type in the device PTRs and.
So this is for the people that really want to do some CUDA stuff?
Yes. This is, for example, the real case scenario would be I have my application and I'm using OpenACC to port several parts and put them on the GPU, but at some point you end up using, okay, I need this kernel to be really optimized because it's really crucial for my application. So at some point you might decide, okay, I want just this kernel to write it myself on CUDA. And then the rest of your application will be in OpenACC. So you need a way to interoperate between the two. So that's the idea. Then in the next hands-on, I will show you how you can call, not in the next, after the next. I mean, I will show you how you can call CUDA functions from, or it's not exactly this. Here is you do your memory management. Then I will show you how you can continue to use OpenACC even for the data management and just pass the OpenACC device pointer to the CUDA function. That's another case. I will showcase this also in the next example where I'm going to show the MPI RDMA version and then the kublas. So coming back to your question, then you have to do your copy out basically yourself. And this is copy to host, which is basically the CUDA copy, I don't remember the exact call, from device to host. So you have to do it yourself. So I can run it. I can put it to run as the OpenACC CUDA. Yeah, you need again. Okay, just let me get the number here, and I will.
Did you recompose it?
I haven't changed anything, so it compiles all the versions. So this since it's in the solutions. So for those that, okay. Okay, this is what we wanted to keep up showing. It's basically whatever you had before, but instead of doing present, you just replace that with device PTR. And
Private is the default anyway, right? Private, IJ.
Yes, it is a default, and if I didn't put that, then I think the Cray compiler was complaining, so I just put it there to get rid of the. Sorry for that. So here, which version? OpenACC CUDA is, okay, we're again at the same performance. I don't know, we're even faster. Before we were at 0.95, now we're at 0.56 seconds. So it's like 10 times faster than the OpenMP version, CPU-only version. And we're still faster than the OpenACC data management, I suppose, is just because, not because we're just copying with CUDA, it's just because we can do this clever swap of pointers that we couldn't do with the OpenACC version. And at the end of every iteration, we had to copy back instead of swapping the pointers. And this has given us like twice the performance. Because copying is memory bandwidth bound operation. So now I could show you the MPI version. So if do you want me to go to the other screen with a code listing? Okay. Okay. Okay, here is the MPI version. Okay, much more complicated at the beginning, setting up the communication stuff. Let's go to the interesting part. Again, here, nothing has changed from the sync node version. Again, here, the same thing. You see, create and copy out as we have had it before. the field GPUs, okay, then we have some MPI stuff. Then we start the iteration loop here. And that's the critical part that I want to show you. So what's happening here? So here is basically what is the communication part, right, of the NPI. We have I receive and I send, and we're exchanging the boundaries. And then we wait for all these things to finish. So now, in the normal case, what I would have to do is the x0 and x1 pointers I have allocated up here. Okay, here, those pointers reside on the arrays reside on the GPU, right? So what normally I would have to do, I would have to do an ACC update and update the host copies with what has been computed on the GPU, and then do the MPI calls. However, I'm doing but I don't want to do this. These are additional copies that I've told you before, and that's performance critical. So I want to instruct somehow the MPI runtime to use the device pointers, because, for example, the Cray MPI understands if you pass it a device pointer, then it will understand this and will use this optimized data path and will copy data directly from the GPU memory to the network to the network card. So how you do this with OpenACC? So there is this AC host data directive, and you put that clause here, the use device, and you're basically saying, okay, look, for this next block of code that I am putting here, for x0 and x1, use the device pointers. So for this block shown there, the MPI I receive and I send calls will receive pointers to the device. And then the MPI runtime will understand this and initiate the fast data path. So that's the trick. And the use device, the directive says it just says that for the next region, use the device pointers. So because normally x0 and x1 refer to the host copy. In your code, for example here, whatever you see, I mean the x0 and x1, normally they refer to the host copy. But here, when you use the use device, you say that for the next block of code, use the device pointers. So this is basically the trick, and I think, okay.
So it's necessary to always write both keywords, both data?
Yes.
So they are kind of...
Yeah, the host data is the directive, and then the use device is the clause. So the normal syntax is you have a directive like ACC data that we have. Data is a directive, and then you have the clauses, which is copy in, copy out, or whatever. Here is host data is the directive, and use device is the clause, like the arguments to the directive.
And in OpenACC, can you also do this?
Mandas, I'm not sure. So meanwhile, and nothing has changed in our diffusion to the HPP, right? As we had it before, nothing changes. So here you do that, and let me let me also run this, and then we can try, instead of doing this, do the update of x0 and the x1 instead of doing this and see what's going to happen. So the job bots here is, I have to change to 2. And then I can use I'm putting a large one, and then if you want, if you run on a Cray machine, right? And I mean, or or that the MPI ECH implementation supports RDMA, then you have to export this variable before running. If I uncomment this, if I comment this out, then I will get a segmentation fault, and I can show you. And yeah, so now I'm gonna run this thing, and let me just open here for you the Open MPI version. So has it finished? Yes. Okay, it's 0.733 seconds. And on the single node, we have 0.9 for that version. Okay, we don't have perfect scaling. But yeah, that's for demonstration purposes. So what we could try right now is, instead of doing this, try to do an update without getting the optimized path. So, okay, I will comment out the, so it's pragma ACC, and I think it's update. I should check. X0 from 0 to buffer size, and x1 from 0 to buffer size. No, I think it's update host, sorry. It's update host. But just let me check the syntax a bit, because I need to, yes, update host. So here I'm saying update host, and then you have to update the device basically as well.
Could I interrupt you?
Yes.
So for the host data use device, if you want to do same things on OpenMP, you just create a data region, so OpenMP target data, and then specify use device pointer and then list it there.
And this will also make data go directly from GPU to MPI?
Yes.
But yeah, that's, there are two parts. One is the OpenACC, OpenMP part, which you just, the runtime, you say to the runtime, use the device pointer, and the next part is, for the next part, responsible is the MPI implementation. So there are two parts, two separate parts. So on Daint, you can use this. There is the MPI implementation supports this optimized data path.
The default one.
You just, as I showed you, you just have to enable to export this variable.
Yeah, but in terms of loading different modules.
No. You don't have to do any load different module. You just have to export this variable. Okay, and then I have also, after I computed my, after I got the, I have to do a Pragma AC update device so that then I can compute on the device. So this, let me check if that makes sense, please tell me. So here the non-optimized version would be, before doing the communication, update the host copies from what's on the device. After the communication here is finished, update the device copies with what you have gotten. So let's see how this works. Okay. No, I didn't compile.
So if I understood it correctly, you now want to do it without the using the actual data on the GPU, right? You copy it to the host.
Yes, I'm copying it to the host, and then from the host to the device.
So then you also want to remove the environment variable in your script?
Okay, I will.
I mean,
theoretically, it shouldn't be a problem, but
no, it's not a problem. But if you do not want to use that functionality, you should.
Yeah, let's see how
remove it.
This looks like. Okay, it's running. Okay, it appears to take more time. Because we're doing that, I think, for every iteration. So there's lots of copies in and out. So let's see. Oh, it's really slow. It's really slow. But let's see if we have. No, I need a smaller. I mean, to plot it, I need a smaller test case. But this is really slow. But before doing that, I want to check that we have done everything correctly. So I'm gonna submit a very small even the small test cases. Okay, yes, this is what we expect because we just print the rank 0 here. That's why we don't see it on the top. So the update host update device works correctly, but you've seen here there is a tremendous difference. So because there are lots of copies. So it's not only from host memory from device memory to host, but then you have to copy from device memory to MPI buffers, and then from MPI down to the network card. So there's lots of copies, and yeah, that's why. And with the RDMA, it's just the kernel. You instruct the kernel, and kernel takes the data from the GPU right to the network card, and that's it. So that's why you see from 0.7 seconds we had before, we went to like 17, because we do that in every iteration. not plot. So let me, yeah. So yeah, we do those copies, we do them for every time step. So there are lots of data going back and forth. Okay, we have like half an hour, so I can show you the next hands-on, which, well, it's less complicated. And I'm gonna showcase this GEMM example and how you you can call a Kublas method. Okay. So this is in the GEMM folder. And okay, I'm gonna show you a bit the code. So okay, let me. Okay, there's lots. Unfortunately, this example I have it only C++, and there is also some C++ salt in this example, so to make it a bit easier, the interface. So here is the naive kernel. I'm not even running it because it's too slow when you try to increase a bit the array size. And any ideas why this is very, very slow?
Can you print like the PWD or something that we see?
Yeah. It's, well, it's for your, it's in exercises. So OpenACC train exercises OpenACC GEMM.
AXPy, common diffusion and shared.
There's no GEMM? Okay. Okay. Okay, let me check. So exercises, OpenACC. Have you? But I am now on the master, and I'm really curious. Because, okay, let's see what's really on the master here. You're really right. Okay, sorry. I mean, I will push right now, and then you can pull it, okay? Oh, that's really strange. Okay. Okay. So now, yes. So now it should be there. Sorry for that. So now if you just do git pull origin master, then you should get it, but tell me if you have problems. Okay. So did everybody got it? Okay, so let me show you then how it looks like. So I have, here are several versions of the GEMM. And okay, here is the naive one. So if you see the text, the math textbook, this is what you would write. So what's the key problem here? I mean, if you try to write this, it will be extremely slow. This is what you would see from the math textbook, basically. But if you write that on a processor, it will be extremely slow. So do you think, I mean, something happening inside the innermost loop? So, what? No, that's not a problem, and it could be on a register. So it's.
Well, I remember there are some redundant accesses to E and
So look at the running loop variable in the inner loop. So it's k, right? Okay, look at the axis of the C array. The C array is the elements of the C on the A array. They're accessed serially, right? It's here in C. So it's every time you update you go element by element. Look at the B array. You're always at the innermost loop. You're doing strides of n. So you go to the next row of memory, the next row of memory, the next row of memory. So that basically means thousands of cache misses in your tight internal loop. That's why it's completely inefficient, because you have strided accesses there. So you see it's B of k by n plus j. But the running variable is, the running loop variable is k. That's perfect for the A array, but for the B array is disastrous. So that's, well, the simplest, I mean, optimization that you can do is just reorder the loops. They're independent, so you have to do a bit of some adjustments around and there, but now you just swap the loops. You have ikj instead of ijk, and then you have much better pattern. So these are our baselines. Well, the naive, I don't even run it, basically, because if you just put a large array, a bit larger array, it will take ages to finish. And then I have the DGEMM OMP version, which, parallelize over the last two loops and collapses them. And I don't know if this is the most efficient, but at least it's a first version that anybody could write. And then it's so up to this point, you have them also in the exercises. And then it's the OpenACC version. Okay, I should show the solution, sorry for that. Should go directly to solutions, GEMM, here. Okay, the OpenMP, and here is the OpenMP version. Again, all the versions are based on the loop reordered version. Okay, and this is what you would do, I mean, for the OpenACC version. So it's AC parallel loop. Again, you collapse the two outer loops. Alpha and beta are first private because you want them to be copied. First private, it means that they take the value they had before, and there is a private copy of them in each thread. So, but they're not randomly initialized. They just take the value they had outside this region. And then you copy in the A array, you copy in the B array, and then you copy in and out the C array, right? And then you do also reduction on the final product there. And that's what you get for the OpenACC. So let's try this out, and then I will show you how you can call kublas, because you don't want to write your matrix-matrix multiplication yourself. Okay, now I will compile. Okay, yes, apparently. So, cd. Okay, that's a warning. Don't care a lot. So now I will, let me remember how I treat here I think again I'm using power of 2, right? Or, no, I'm not, yes, I'm using power of 2 things here. So, okay. So now I srun minus reservation open minus c GPU minus t whatever minus t5 and GEMM, and I will put how large array? So I will put 12. I will put 256 by 256. What I have done wrong? No, I'm canceling it. I want also to put OMP new threads 24 so that the OpenMP version will have all the threads. So now let's see.
So now we are running both.
Everything. So you will see also the kublas version here. So I'm running all the kernels and checking their results. So okay, I should increase a bit the array, because you see here, well, even the serial version is quite fast because everything is in the cache, in the L2 cache. So I will increase a bit the arrays. So I will go for 1K by 1K arrays, and let's see. And you see also a tremendous, overhead with the GPU and kublas version, if for so small arrays, because we just copy in the data, set up the kernels, and copy out, so it doesn't make any sense. So let's see now, this should be faster. Why we wait? I don't know. Why it has to wait? Okay. Okay, so now you see it has started to make some sense. Again, the multicore beats the GPU because the array is still relatively small. Let's try some larger. So the outcome of this is that you have to have very large data sets that it makes sense to put them on the GPU. Okay, that's better. Still, here for the GPU, I'm counting also the data transfers. So it's not the pure kernel time. But if I increase it further, you will see, still, I don't know for what reason my version beats the kublas, but I think when we increase further, probably it will get. So now we have 2K by 2K, oh no, 4K by 4K array, so it will take some time. Oh, I have also the serial. Oh. Okay. Okay, kubeless has started to pay off. So this, we have a large array, 400 megabytes to do matrix multiplication. It's quite heavy. At this point, it starts to make sense to use GPU, at least for my simple implementation with OpenACC, with the data transfer. So the kernel is much, much faster. And then you see kubeless. It's twice as much because they are doing different stuff. So how do I use kubeless? Because I don't want to write another kubeless for matrix multiplication. So, okay, these are C++ salt. You don't need to care. So let's see GEMM kubeless. Okay. So here, okay, ignore this line, is basically picking up the correct function of kubeless. We just go into the kubeless and put the exact version for double or for float. So this is just C++, so you don't care. So again, what should I do? Again, I do copy the data. I have to copy the data to the, because, I mean, the kubeless methods, they just take a pointer on the GPU. So they assume that you have all your data somewhere, and you pass them a pointer in the GPU. So I have to do the management myself. So I'm copying the A, the B, and copy in, and then I'm copying out the C, which is the result. And then I do exactly the same trick we've used for the MPI RDMA with a host data use device. So I'm basically says, look, those pointers that you will see right in the next block, use the device pointers, not the host pointers. So in the next call here, A, B, and C are actual device pointers that they have been allocated and they are managed by the OpenACC. But here I pass the pointers on the on the kubeless method. There is a small cheat. I mean, I'm cheating a bit in the call here, not in terms of performance, but just in terms of the arguments, because kubeless assumes column-wise data layout, but the way I have initialized my arrays, it doesn't matter. So, but in a real application, you will have to keep that in mind. That kubeless assumes column major arrays. Here, I didn't want to go through transformation and stuff, so I'm just, that's why I'm also computing the transpose instead of the standard matrix multiplication. But nonetheless, despite the transpose step, despite the copies, using kubeless is much faster than even my example and even, I mean, the CPU. So this is a way that you can call, for example, kubeless methods, or you could, don't see it like kubeless. I mean, you could have in your application, you need a kernel that you will write it yourself, and you, in your kernel, you can assume that the arguments you take are actual device pointers, and then go on, do your optimized CUDA method, and then the rest of your code, you're using OpenACC, and with this thing, you can call your optimized kernel for just a specific part. You don't need to write all your application in CUDA. You may also just need to write only the compute-intensive parts that you really need to optimize them for it. So yeah, these are all my exams. I think we're almost done. It's also 10 to 5. So any questions? I will just now, now in the afternoon, I will push the solutions into the master so you can pull them so that you can have them.
And we should save all this stuff today. Tomorrow I guess
Yes, today Piz Daint won't be available. So if you want to try things, I think the reservation is valid until 6 p.m. or 7 p.m. today. In case you want to try things even from here or from your or later, I think you have just an hour still.
And the repositories?
The repositories will be always available, so
Okay.
you will have it.
So we can. How long will it be available?
The repo will be there. At some point, I may, with the repository, I'm gonna do some point later a release so that to mark this point that it was the course, so you can always reference it because then I can update it with other material and stuff. So, but the repository will be available, so you don't have to hurry and take it.